In this video, we're going to talk about some quantitative demand analysis. So one of the things that you do in managerial econ is that you use data to help make business management decisions. And elasticity is one of the concepts that is really useful. So in a principles class or even an intermediate micro class, we always cover elasticity, but it's hard to emphasize how important elasticities are when you're actually making business decisions. So what we need to do is just kind of review some elasticity stuff, talk about how elasticity and total revenue are related, talk about elasticity and a demand curve, and then talk about how you can actually estimate some elasticities. So let's start by thinking about just price elasticity of demand. The notation that we're going to use is going to be E to stand for elasticity, and then the elasticity of demand for good Q with respect to the price. So some textbooks call it an own price elasticity. We would define that as the percent change. I'm going to use the percent symbol and that triangle to stand for the word change in. So the percent change in quantity demanded of, say, good X divided by the percent change in price of good X. So that's a standard elasticity formula. Percent change in quantity divided by a percent change in price. And let's talk a little bit about how we would interpret that. So if that elasticity, I'm just going to write E for the elasticity here. If that elasticity was, when you calculate it, greater than 1 in absolute value, remember that price and quantity demanded move in opposite directions. So if price goes up, quantity demanded is going to be going down, so the whole thing would be negative. Or if price goes down, quantity demanded would be going up. So again, the whole thing would be negative. Either the numerator or the denominator, one of the two is always negative. So we think about it in terms of absolute value. But if you calculate the elasticity and the percent change in quantity is bigger than the percent change in price, then that ratio is going to be greater than 1, and we would say that that demand is elastic. Demand is elastic. If you were to calculate it and the elasticity is less than 1, in other words, if the denominator is bigger than the numerator, then we would describe demand as being inelastic. And then the last possibility is if you were to calculate the elasticity and it were exactly equal to 1, we would say that demand is unit elastic. And that would happen if the percent change in quantity is exactly equal to the percent change in price. Now, what we can do is we can take that percent change in quantity divided by percent change in price and write out what that looks like. And it would be this. If we wrote the elasticity as the percent change in quantity divided by the percent change in price, and then we write out how you would calculate the percent change in quantity, well, the percent change in quantity is going to be the change in quantity divided by some, usually the starting value, but when we're thinking about calculating an elasticity, we think about using the average quantity. So if you've got two quantities and we want to know the elasticity or the percent change in quantity, let's say, you'd look at how much quantity changes, and then we would divide by the average quantity. For right now, I'm just going to call it Q. And then we would divide that by the percent change in price, which would be the change in price divided by the average price, which I'll just write as P. Now, what I can do is I can write it, can simplify this by writing the numerator, which is the change in Q divided by the average Q, and then multiply by the inverse of the denominator, which would be P times the change in P. So all I've done is invert the denominator and multiply it by the numerator. And then multiplication is transitive. So what I can do is I could reverse the order that I write these two in. So for example, 2 times 3 is equal to the same thing as 3 times 2. So I can reverse the order of these and write it this way. The change in quantity over the change in price multiplied by P divided by Q. So that's another way to write the elasticity. And that might look familiar to you if you've ever had any calculus, but even if you haven't, you don't need to worry, because what we usually do is we usually write that this way. Instead of writing the delta, the Greek letter D, I'm going to replace it with just an English D and say that the elasticity is equal to dq over dp times P divided by Q. And now this term right here, that change in quantity when you change price, this is the slope of a demand curve. Okay? So if we take the slope of the demand curve and we multiply it by a price and divide by a quantity, we're going to get an elasticity. So this is another way to think about elasticity if we were calculating it at a specific point on a demand curve. And I'll illustrate that here with a demand curve. Let's suppose that we had a demand curve that looks like this. Q, let's say quantity demanded of good X is equal to 80 minus 2 times the price of good X. Now that's a demand curve. If we were to invert that and solve it for P, which would be easy, if we were to do that, we would have the inverse demand curve. It would still represent the same relationship between price and quantity. But when we look at it right here, we would just call it a demand curve because it's solved for Q. So we could take the price and we could plug the price in here on this side, and that would tell us quantity demanded. Okay. Now the slope of this, the slope is equal to dq dp. This is the notation that we use to indicate the slope. It says, how much does quantity change when you change P? And the answer is that for every time you change P by 1 unit, it changes Q by -2 units. So the slope there is -2. Okay? And you could see that if you just don't even think about this. Let me just say that if you know how to take a derivative, the derivative of this with respect to P, which is this notation, is just -2. But you don't need to know how to take a derivative to understand that this function here is in slope-intercept form. Here's the intercept, and then that number right there is your slope. It's -2. So you don't need to know anything about the calculus of it to know that the slope is -2, and then just remember that this is the notation we use to indicate the slope. So there's our slope. It's equal to -2. Now what I'm going to do is I'm going to think about a picture here of this demand curve, and I'm going to draw the demand curve right up here. And then down below that, I'm going to draw another picture that shows what revenue looks like. So up here, we're going to have our inverse demand curve. Okay. This is how we would normally draw a demand curve. Now we've got to be careful because the way we have this demand curve specified, that indicates that we're putting Q on the vertical axis, but I'm going to draw this with Q on the horizontal axis. In my bottom picture, I'm going to put total revenue, and I'm going to put Q on the horizontal axis. And this is why I want to draw this way. Now, let's go ahead and take this function, and I'm going to invert it. So I'm going to write it more simply. I'm going to say this, Q equals 80 minus 2P. I'm going to drop the superscripts and subscripts, and I'm going to solve this for P. Solve for P. That's going to allow me to draw it right up here. Okay. So I'm going to move my 2p over to this side, and I'm going to move the q to that side. So I get 2p equals 80 minus q. I want p by itself, so I'm going to divide by 2. That's going to leave me p over here. It's going to be 40 minus q over 2. There is, I'm just going to circle that thing. There is what I would call the inverse demand curve. And this is the one that we graph in this picture. It's got an intercept of 40. It's got a slope of negative 1/2. So you go down 1 over, you would go down 2, down 1 over 2, down 1 over 2. We've got rise over the run, and our slope is negative 1/2. Took me a second to kind of get my head wrapped around that. By the time, so every time you go down 1 over 2, down 1 over 2, by the time you've gone down 40, you'll have gone over 80. So this thing comes down and hits right there at 80. If we were to invert this, we would see that it has an intercept, vertical intercept of 80. Okay. Now I'm going to put, so let's see, right in here would be, let's say, what, 40, 30, 20, 10, 50, 60, 70. So I want to be kind of careful with how I graph this. So I'm going to designate my horizontal axis kind of carefully. 80 is right out here. I want to put 80 down here. Now, my vertical axis is going to be, so right in there's 20, here would be 30, here would be 10, of course that's 0, and then I'm going to have 5s in between there. Okay. And so if I were to say plug in a quantity of, let's say 70, if I plug in a quantity of 70, then it would be 70 divided by 2 is 35. 40 minus 35 would be 5. So at a quantity of 70, then I would hit right up here at 5. And at a quantity of 60, I would hit at 10. And a quantity of 50, I would hit right there at 15. So that's what this thing looks like. Okay, I'm trying to be real careful with drawing this precisely so that we can do some stuff with it. So there's what it looks like. Now what we want to do is we want to kind of think about at each of these points right in here what the elasticity would be. With this function for elasticity, I can easily calculate the elasticity at any of these points. So here's what we're going to do. We're going to create a little table over here where I've got, let's call this point A, point B, C, D, E, F, G, H, I. And I'm going to put point, and we're going to calculate the elasticity to each of those points, A, B, C, D, E, F, G, H, I. Now, let's figure out what the price is at each of these, because that's part of what our formula looks like, right? Our price at point A is 0. And our price at point B is 5. So this thing's going up by 5 each time. 10, 15, 20, 25, 30, 35, 40. And then my quantities at point A, my quantity is 80, right? And then at point B, it's 70. So that thing goes down by 10 each time. 60, 50, 0. Okay. Now, let's figure out what elasticity is at each of these points. If I were to calculate elasticity, so let's say at point A. So if I were to plug in what's going on at point A, my slope is -2, my price is 0, and my quantity is 80. Well, 0 up here in the denominator means that the whole thing just ends up being equal to 0. The elasticity is equal to 0 right there at the end point, at point A. If we were to look at the elasticity at point B, well, now my slope is -2, my price is 5, and my quantity is 70. So if I do that, what I'm going to get is -0.14. Now I'm going to fill in the rest of these, this column for elasticity, and you can verify, you probably should verify that when you plug in the price, the quantity, and -2 for the slope, that you get the same numbers. But here's what they would look like if we did this. It's -0.33, -0.6, -1.00. That happens right there at point E. And then -1.67, -3, -7. And then if you get up here and you try to calculate it at point I, you're going to run into a little bit of an issue because you've got a quantity of 0, and that quantity is down there in the denominator. You can't divide by 0 or bad stuff starts to happen in the universe. So you would need to take a limit as this goes to 0, and what you would see is that this elasticity goes to infinity, -infinity. So here's what we see. Points A, B, C, and D, these points down here, this range of the demand curve, what we see is that the elasticities are all less than 1. That means that demand is inelastic. This is the inelastic portion of the demand curve. Right up here, point E, it's unit elastic, right? It's equal to 1, unit elastic. And then over this range, that demand curve is elastic. At points F, G, H, and I, the elasticity is greater than 1. Now, let's do one last thing. We want to know what's happening to total revenue as we move along this demand curve. So let's just calculate total revenue. Let's start by doing it at the end points. Well, at the end, total revenue is just price times quantity. And if we're here at point A, well, then we're selling 80 units, but the price is 0, so our total revenue would be 0. If you're selling stuff for $0, you make 0 money. And down here at point I, where we're selling 0 units, we also make $0 of revenue. But then if we're here at point B, we're selling 70 units for $5 each. That's $350. If we're selling 60 units at $10 each, that's $600. 15 times 50, that's $750. 800, right? 40 units times 20. 25 times 30, that's also $750. This one's $600, and this one's $350. Here's what happens. Our total revenue is 0 down here where we're selling 0 units. It's also 0 when we're selling 80 units because we're charging a price of 0, and it's at a maximum right at the middle. So here's what total revenue does. It comes up, it reaches a maximum, and then it goes back down. So here's the general rule that you've probably heard in a principles of macro class or micro class. And that is, if we're down here on the inelastic portion of the demand curve and we raise price, if we're moving this direction, we're raising price, which is causing our quantity to go down. If we're raising price on the inelastic portion of the demand curve, our total revenue is going up. But if we continue to raise price in the elastic portion of the demand curve, our total revenue starts to go back down. So we're raising price by moving from here in this direction, okay? Because remember, there's an inverse relationship between price and quantity. So as price goes up, quantity's going down. And so that will help you understand that rule, that if you're raising price, if we're in the inelastic portion of the demand curve and we raise price, well, because people don't respond very much, our revenue is going to go up. But if we go past that point where demand is unit elastic and we continue to raise price, now that hurts us because our total revenue is going down. Let's talk about a couple of special demand curves before we kind of move on and talk about arc elasticity. Two demand curves that you would have seen before, just kind of the two special cases. We can talk about the elastic and inelastic portion of a demand curve, but remember that a demand curve, the steepness of the demand curve, is also measured by elasticity. So for example, if we had a demand curve, if we go back to putting price here and quantity there, and we have two demand curves, let's call this one A and this one B, we would say that demand curve B is more elastic than demand curve A. Another way to say that is that demand curve A is more inelastic than demand curve B. Finally, let's talk about perfectly elastic and perfectly inelastic demand. So a perfectly elastic demand curve looks like that. If we had a demand curve that looked horizontal, we would describe that demand curve as being perfectly elastic. Let's squeeze one more demand curve in here. If we had a demand curve that was vertical, like that, we would describe that demand curve as being perfectly inelastic. So now what we're going to do is we're going to clear this off and we're going to talk a little bit about what I was describing here with the averages. So let me clear this off. Let's think about how you would estimate an elasticity in the real world. So we're going to talk about estimating a demand function in a subsequent video, but let's think about kind of how you would estimate an elasticity if you don't have say a slope that's been estimated from a demand function. In that case, you would calculate what's known as an arc elasticity. So if you knew a price and the quantity that went with it, you knew two prices and the quantity that went with those two prices, then you could easily calculate the arc elasticity by thinking about change in quantity divided by the change in price multiplied by the average of the prices and the average of the quantities. So this would be something if you had a price and a quantity, another price and a quantity, you could figure out the difference in the quantities, the difference in the prices, the average price and the average quantity, which is typically what we do in a principles of micro class. That's usually what we do. So we're going to be thinking about this as being the basic way to estimate an elasticity in the real world. But if you can estimate a demand curve and pull out that slope estimate, which we'll talk about later, which would take the place of this thing, then you can calculate elasticity at points on a demand curve like we just did. Let's just briefly review what determines elasticity. Remember that the key thing that determines whether demand is elastic or inelastic is the availability of close substitutes. Availability of close substitutes. Within that, we could think about goods that are necessities versus luxuries. If we're talking about necessities, there aren't very many close substitutes for necessities, so demand tends to be relatively inelastic. If we're talking about luxuries, luxuries are typically a thing for which there are lots of substitutes, fairly close substitutes, so demand tends to be relatively elastic there. We can also think about the definition of the market. Definition of the market. Whether we use a broad definition or a narrow definition, that's going to determine whether demand is elastic or inelastic. And that has to do with the availability of close substitutes. If we use a very narrow definition, there are often more substitutes available. If we use a very broad definition, there are fewer substitutes available. Consider the broadest definition for, let's say if we just talk about food. It's a very broad definition of a market. It includes all food. There's no substitute for that, really. So demand would be relatively inelastic for those very broad definitions. We could also think about the passage of time. That's something that determines whether demand is elastic or inelastic. And then we could think about, finally, the share of the good in the consumer's budget. I'm just going to say share of the good in the budget. Now let's think about how that works. So if you think about how much you respond to the price of something that doesn't consume much of your budget, you probably don't respond very much at all. So the example I always use is if you go to the store to buy some gum, probably what you do is you don't really probably even pay attention to the price. You just look at the flavor you want and you grab it and you put it up there and you buy it and you never think anything of it. In fact, you pay so little attention to the price that the price probably could be higher than it was last time you bought gum and you not even notice it because it occupies such a tiny fraction of the amount of money that you're spending that it's not worth worrying about. So things that consume a small share of the budget, our demand tends to be relatively inelastic. We don't pay much attention to the price. If we're talking about something else, rent or the price of gasoline, something that consumes a larger share of your budget, well, then you tend to be more sensitive to price. So demand tends to be more elastic for those things that consume a bigger share of the budget. Let's think about the relationship between marginal revenue and price elasticity. So remember that marginal revenue is just the change in total revenue when you produce one more unit of output, change in total revenue from, let's just say, one more unit sold. So we could write it this way. The marginal revenue is equal to the change in total revenue when you change quantity. Another way to write that would be let's use D, change in total revenue when you, or that should be R, when you change quantity. So we could replace those Greek deltas with English deltas and it says the same thing. Only this is the same notation that we would use if we were taking a derivative, say. Let's think about how marginal revenue is related to elasticity. So remember, if we're going to think about the marginal revenue curve for a linear demand curve, here's what it looks like. If we've got our price and quantity and we have a linear demand curve, hopefully you remember from a principles of micro class or an intermediate micro class maybe that the marginal revenue curve is going to have the same intercept and twice the slope. So it's going to come down just like that. Now let's think about that. Remember that if this has twice the slope as this, and if we think about the horizontal intercepts right here, this horizontal intercept has to be half the distance to there. In other words, if we were to go straight up from that point, we would hit the exact middle of that demand curve. And the exact middle of the demand curve is where the elasticity is going to be equal to 1. So here's what we can see. We can see that as we're changing quantity, if we're out in this range, right, this is that, the range, remember we were talking right up here, notice that out in this range of the demand curve, marginal revenue is negative. And in this range of the demand curve, marginal revenue is positive. What we can do is we can relate the elasticity to the marginal revenue. Here's how they relate. we don't need to derive this. I'm just going to write it. It looks like this. 1 plus the elasticity divided by the elasticity. So there's the relationship between the elasticity and marginal revenue. Notice that if the elasticity is equal to -1, which it would be right here, that's actually negative. If we plug in a -1, this would go to 0, and that would confirm what we're seeing right here. Marginal revenue definitely is 0. On the other hand, if we're thinking about, let's say, when the elasticity is in between -infinity and -1, marginal revenue is positive. That's right up here. Remember, our elasticity was -infinity up here, and our elasticity was 0 down here. Right? This is the elastic portion of the demand curve. Marginal revenue is positive. If we're thinking about that portion down there, then we're in a situation where the elasticity is in between, ignore that dash there, in between -1 and 0, and that's where marginal revenue is negative. Let's talk about the cross-price elasticity of demand. Cross-price elasticity. So remember, the cross-price elasticity tells you how much demand for this good changes when the price of that good changes. It tells you the strength of relationship between the two goods. Two goods could be complements or substitutes, and the cross-price elasticity tells you how closely they complement each other or how closely they can be substituted for each other. And the equation for those, I'm going to write it as, let's say, the elasticity. I think the notation that our book uses is the elasticity of the quantity of good X with respect to a change in the price of good Y, and that is equal to the percent change in quantity of good X divided by the percent change in price of good Y. And we can write that in this type of notation this way. It would be the change in quantity of good X with respect to the change in price of good Y multiplied by the price of good Y divided by the quantity of good X. That's another way to write it. Let's also talk briefly about income elasticity. So income elasticity is the percent change in demand when you change income. I'm just going to write it this way. The elasticity of good X with respect to a change in income. The textbook we're using uses M for income, and it would be the change in quantity of good X with respect to a change in income multiplied by income divided by quantity of good X. And the sign of that would tell you if we're talking about a normal good or an inferior good. You've seen that before. The sign of this would tell you whether we're talking about complements or substitutes. There are other elasticities we could calculate. For example, we might estimate a demand curve that has expenditure on advertising in it. And if we do that, we'll be able to calculate an advertising elasticity. Let me just show you what that would look like. Advertising elasticity, we could define this way. I'll say the elasticity for good X with respect to a change in advertising for good X. We'll use that notation. That would be the change in demand for good X when you change advertising for good X divided by advertising multiplied by advertising divided by quantity of good X. So that would be a way to figure out how changes in dollars spent on advertising the good affect demand for the good. Now let's talk about how we would get these elasticities from a demand curve. So usually in a principles class or even an intermediate micro class, this is kind of the extent of the discussion that we would have on elasticity. But let me show you how you would actually put this into practice. What you would need to do is you would typically need to estimate a demand curve. You would need to use regression analysis to estimate a demand curve. And we'll talk about that here in just a second. Well, actually, we'll talk about it in a later video. But let's talk about getting elasticities from a demand curve. That's how you actually take all of the theory we're talking about here and put it into practice. So let me define a demand curve, a general demand curve. This will look complicated when you first think about it, but it's actually not. So let's suppose we had a demand curve that looked like this. Quantity of good X demanded, right? That's the number of units that people buy of good X. It's going to have some intercept, which I'm going to call alpha naught. I'm just going to put a little 0 down there. Alpha is going to be something we're going to estimate. You can think about it, so if I had a demand curve that looked like this, Q equals, let's say, 80 minus 2P. I think that's the demand curve we were just using a little bit ago. 80 would be this number right there. Okay? And then I'm going to say plus alpha X times Px. Well, so if I were to make this consistent with that, then alpha X would be -2, right? It tells me how much does a change in the price of good X affect the quantity purchased of good X. So that's just something, but I'm not going to specify it because what I want to do if I'm going to get a demand curve from an elasticity from a demand curve is I'm going to estimate the demand curve. I'm going to let the data tell me what that should be. Okay? That's where it would have come from in a demand curve like this. But now remember that there are other things that affect demand. We call them the determinants of demand. Things like income, right? Things like the prices of other goods. Things like advertising. So we want to put that into the demand curve. So I'm going to say plus alpha y times py. So this would be, suppose good y is a substitute good, or maybe a complement. Well, the price of good y also affects demand for good x, so I'm going to put that in there. And then I'm going to say, well, we need income. I'm going to say plus alpha m times income. And then we could have even something else. We could put advertising in there. Right? We could put, so let's say maybe we have plus alpha A times the amount spent on advertising. And we might think about putting other things in there. There might be some other variables that might belong in this demand curve. Well, in this case, these things right here, this slope of the demand curve with respect to the change in the price of y, this thing would be right there, alpha y. So if I were to estimate alpha y, that would be giving me an estimate of the slope of the demand curve with respect to a change in the price of good y. This term right here, how a change in income affects Q, that would be this term right there. Okay, so let me write out some of these. Change in quantity with respect to the price of good X. This is just the slope of the demand curve. That's equal to alpha X. That's that one right there. And then if we had a change in quantity of good X, all of these should have good X down here, with respect to a change in the price of good Y, well, that's equal to alpha Y. That is right there. So if I were to estimate this function and I come up with a parameter estimate for that, that's what I'm going to use right there in that formula. And then if we had a, let's suppose we wanted the change in good X with respect to income, that's equal to alpha M. Or if we wanted the change in good X with respect to advertising, this term right up here, that would be my alpha A. So you can see where these things come from. We can build a demand curve that's more complicated than just this nice simple demand curve, because actually demand is more complicated than just that. I'm going to clear this off, and then we'll take a look at what a demand curve might look like if it was nonlinear. So let me clear this off. Let's take a look now at a nonlinear version of a demand curve. And this is going to initially look very complicated. It turns out that it's not as complicated as it looks once you make a simple transformation of it. So let's suppose that our demand curve takes this form. Suppose we had quantity demanded of good X, and it looks like this. I'm going to put C here. And then I'm going to multiply by the price of good X, but then I'm going to raise that to this power, beta X. You'll see why I'm doing that here in a second. And then I'm going to write the price of good Y, and I'm going to raise that to beta Y. I'm going to multiply by income, and I'm going to raise that to beta M power. And then I'm going to multiply by advertising, and I'm going to raise that to the beta A power. Now that's a very different looking demand curve than probably what you're used to thinking about, because it's still got the price of the good itself in it. It's got the price of a related good. It's got income. It's got amount of advertising dollars as a argument of it. But it's all multiplied together, and it's got these weird superscripts, or these weird powers, excuse me. Now, this would be something that would be very challenging to try to statistically estimate as it is, but what we can do is we can take a simple transformation of it, and we can turn it from something that's highly nonlinear into something that is actually linear. And the way that we do that is we take the natural log of everything. Take the natural log. Hopefully you remember the properties of taking the natural log. Actually, if you're listening to this, you're probably thinking to yourself, no, in fact, I don't remember the properties of natural logs. So you may need to just brush up on that. I'm not going to go through all of the properties, but if you take the natural log of this, here's what you're going to get. You're going to get the natural log of the quantity demanded of good X is equal to, if we take the natural log of this big term, it turns out that you can conveniently break that in. The natural log of a product is equal to the sum of the natural log of each of the terms. And then if you've got the natural log of something to a power, you can take that thing that's in the power and you can move it down to the front. So I'm going to use those properties. You're going to get the natural log of C plus, then I'm going to get the natural log of this term, but then I can put that power in front of it. You're going to get beta X times the natural log of the price of good X. And then you're going to get plus beta Y times the natural log of the price of good Y. And then you're going to get plus beta M times the natural log of income plus beta A times the natural log of advertising dollars. And this term right here, I'm just going to call beta naught. This is what we call a log linear demand. Log linear demand curve. You can estimate it using just regular regression techniques. The only thing that you have to do is you take the natural log of your quantities and the natural log of the prices, and then you estimate these parameters. And in our video on regression analysis, I'll talk about how you would actually estimate those parameters. It is not hard. So you can take a nonlinear demand curve and you can make it linear by taking transformations. And this isn't the only thing that you can do. There are some other things that you can do. But for what we need to do right now, we're going to leave it at that. And I'll see you in the next video.